group was sponsored by Microsoft, which we are very happy to have two giants for supporting our group. So please enjoy and see you later.
Okay, hi everyone. My name is Wei Chen. I'm a machine learning scientist from Amazon Development Center, Germany. I work in the natural language processing team, as you might already know. So today I'm going to talk about k-face extraction. In particular, we introduced the series array, which is a new algorithm, a new method we introduced this year. This is based on a paper we published this year at ASAL. I just learned that while eating a pizza, that the people's background is pretty diverse here. So if in the talk there's something which is uncertain, you have a question, please stop me and ask the question. I essentially prepared the talk like if I would go to a machine learning conference, this is how we're going to do it. So this is a joint work with Natalina, who was an intern with me last summer. So k-face extraction should be familiar with most of the people here. And for example, when you read a scientific journal, normally what you see here is a title and you got an abstract, and you see that some of the key phrases extracted. The idea really is that you don't have to research all the paper to have a good idea what the paper is all about. Now, k-face extraction has application beyond just academic settings. They also have commercial applications. So here, for example, is a page, TripAdvisor. It's a hotel page, where you can see here that the key phrase is extracted from the reviews of the hotel. So the idea that is you don't have to read through all the 1,000 reviews to have a good idea about this hotel. And by the way, this is a hotel close to our office in Berlin, just in case you visit. You could actually try this one. Now, there is some application of k-face extraction in Amazon too. I will talk about it at the very end of the talk. So what is k-face extraction? Essentially, it is just a way to find a collection of phrases that in a document that will give you kind of concise summary of the text content. So here the input is essentially a text document. We only consider text. We don't consider images and sound, not yet. But in this setting, we only consider text as input. And then the output is just a set, also a ranking of phrases. Now, to evaluate how good your algorithm or any algorithm do in this setting, what you do is normally just compare what you extract with the set of phrases or ranking of phrases annotated by human, using the standard information retrieval measures such as position, recall, F-score, and so on. A typical key phrase extraction algorithm works in two steps. In the first step, what it does is that we first using some heuristics to select, say, the candidate phrases. So basically a set of candidates. This is, for example, here, I have a text document. These are the candidates we selected. And then in the second step, we basically trying to pick key phrases from this set of candidates. Or say we rank them according using some kind of machine learning approach. For example, in this example, like these three finally be selected as the key phrases of this document. So for the first step, there are a number of heuristics often used. One is using noun phrases selected using part-of-speech tagging. So here's a simple kind of part-of-speech tagging kind of formula, which we say we select 0 or more adjectives followed by 1 or more nouns. This is my candidate. There are, of course, other heuristics as well. For example, either thing to do is just simply select phrases that doesn't contain any star words, some predefined star words, or predefined, say, function words in English. Oh, I should say that in this talk, I will consider k-face extraction examples in English, but the basic idea applies to other languages as well. So this is the first step. We select a list of candidates, and in the second step, we're using machine learning approach, supervised or unsupervised approach, to determine which of them are really good key phrases. There are, of course, supervised and unsupervised. In the supervised case, there are people do binary classification, because if you have a candidate, then the question is this candidate a key phrase or not? So this is basically a binary classification problem. There are also people who do pairwise ranking, which the idea that is somehow I found an idea to, some supervised way to rank these different candidates, and then I just take the top of them. So in this paper, or in this talk, we consider unsupervised case where we don't need any human labeled data to train a classifier or model. We don't need any labeled data. And essentially, this approach can be considered as kind of a mix of the graph-based ranking and topic-based clustering, which I will talk more in the following. So in a graph-based approach, so this is basically kind of the underlying idea. Essentially, the assumption made here is that a candidate key phrases is important if it is related to other candidate, which is also important. This is the basic idea. What it typically does is first I build a graph, a word graph, where based on the word in the documents. So here all the words are the word in the document, and then the edges essentially indicate that the relatedness between any two words, if these two words are related or not. We'll talk about this later. Then after you build a graph, let's say you have a graph, what you do is to do page rank, or to do random walk on this graph. So after you do the random work, you basically have some kind of a ranking of these words, or some score of the words, and then you can use that score to define the score of your phrases, and then in turn to select the key phrases. I will get into detail later, but this is actually the general idea to do like random work.
So is this
sure
graph built on one document or on the complete set of documents?
Oh, that's a very good question. Essentially, normally what people do is basically you build the graph based on individual documents because that's faster. I mean, you could also build a graph on the entire web, but that takes a lot of time. What you do normally is you can build a graph based on an individual document, the document you're interested about, but you can, in the meanwhile, utilize all the other information you collected from the other corpuses while you're building the graph. Right? But that's a very interesting question. So, okay, let's. One of the state-of-the-art approach on the graph-based ranking for key phrase extraction is this topical page rank idea. So the main idea is really to using the idea of topic modeling, LDA. So LDA is one topic modeling algorithm, and the idea is really use the information extracted from the topic modeling algorithm to guide the random walk on the word graph. And for the people who don't know LDA, so LDA is a topic modeling algorithm, and in the LDA, essentially a topic is a distribution over the vocabulary, and then we assume each document is viewed as a mixture of topics. So for example, if you look at this topic, it talks a lot about director and Oscar, but not so much about probability. So essentially, you could figure this is a topic about movie, for example. And then, in turn, a document essentially can be viewed as a distribution of topics. So that's the basic idea. And something more about LDA. This is, in LDA, this is how we assume that how this document is generated. First, we randomly choose a distribution over topics for the documents. And then for each word in the documents, we first randomly choose a topic from this distribution of topics. And then we choose a word for its corresponding distribution of the words in that topic. So essentially, I built a kind of way to think how my document or how my data was constructed. And based on this idea, how the data is constructed, I can infer, by collecting a lot of data, to basically infer the distribution of the topics and the distribution of topics in the document and the word distribution of topics. So that's the basic idea. Okay, so we talk about the random walk, and one of the most widely used random walk algorithm is the PageRank. So PageRank is the first ranking algorithm used by Google, and essentially the idea is very similar to the assumption which is made by the topic of PageRank, which we say that in topic of PageRank, a key phrase is important if it's related to other key phrases, or say a word is important if it's related to other important words. So here the assumption is the same. They're saying that the more important web page is, that this is likely to be cited by other important web pages. For example, here, you see that the web page C is very important, not because it was cited by a lot of web pages, but because it was cited by another web page, which is very important. So it is essentially the key idea underlying the PageRank, and also the same of the topic PageRank. So this is how topic PageRank works. We have a word graph where the node are the words, and the edge basically indicate how related the two words are. In practice, what you can do is like you have a sliding window goes through your documents. Whenever these two words appear in that sliding windows, you have an edge between them. This is the simplest way you can build the edge. And then essentially, after you build this word graph, you obtain the word score using this random walk formula. For the people who know PageRank, this actually looks very similar to the PageRank formula. The only difference is here that in PageRank, at every point in your node, you can either choose to jump to one of the nodes you collected to, or you randomly jump to another like unknown nodes. Right? This is what we call jump probability in PageRank. So here the only difference here is here, instead of uniformly randomly jump to another places, we basically do the jump using the information we inferred from topic modeling. So this P, T giving WI, is the probability of topic T giving a C the word WI. This is the information you can get from topic modeling. The exact detail of the formula doesn't really matter. I think the main idea, the basic idea, underlying idea is the important one. And then once you have the score of the words, you can get the score of the phrases by simply sum up all the words in that particular phrase. So this phrase is essentially, for example, one of the candidates you have. Right? You want to know what's the score for this candidate. What you do is just you sum up all the words in that candidate. You got the score of the phrase. Okay, and then note that this is the score for this phrase under topic T. And as I mentioned, in topic modeling, you have K topics. You decide beforehand, right? So essentially, then in the very last step, you just need to sum up all the information among all the different topics. You got the final score for the phrase. So, so here is essentially like a graphic summary of topic PageRank. The idea really is first, I will build a word graph based on my documents. And then I do the topic modeling using the LD algorithm to get estimate information for the K topics. And then I run the PageRank K times, one for each topic. And then I got the topic specific K phrase score, and then obtain the overall phrase score. So here, the algorithm works pretty fine, but one thing you'll notice that it does have to run PageRank K times, right? Once per each topic. And this is where our method start to come to play. This is how I will now start to talk about our contribution. And the first contribution of our approach, salience rank, is that while we're still exploring the structure information using topic modeling, but we want to run PageRank only once instead of K times. So by doing that, we save a lot of time. And as I can also show later, that we also achieve similar or sometimes even better performance. This is the first contribution. And the second contribution is give you the flexibility to trade off between we call it topic specificity and corpus specificity. So basically give you kind of more freedom in practice when you're working on a particular application. This I will talk more later. And here is what the basic idea or intuition behind it. On one hand, we wanted some key phrases which are very relevant to particular topics. But on the other hand, we also want to have a set of key phrases which will give you a good coverage about the document as a whole. Right? So put in another word, sometimes the key phrases that are representative specifically or say exclusively for some topics are important. And other times, the key phrases which are representative for the corpus as a whole are more important. Right? So in practice, you need to balance these two concepts. Give an example. For example, if you are looking at a journal paper about machine learning, if you're an expert in machine learning, you're probably interested in phrases that are very specific. But if you're just very new to machine learning, you probably prefer some phrases which are very generic. Right? So that really depends on the audience, depends on the application. Sometimes you want different emphasis at different key phrases. And CNS Run offer you some kind of offer you a free parameter you can choose to basically balance these two competing principles. Okay, so to get a little bit more quantitative, so here is how we define topic specificity. So in particular, we define it using as the KL divergence between PT, which is the probability of topic T, to the probability T giving the word W. What does this mean? So this essentially intuitively means that it matters that how likely a word is shared across different topics. If a word is shared a lot with different topics, the topic specificity is very low. But the word is exclusive for a certain topic, or one topic, for example, the topic specificity will be very high. So here is the example. Assuming that we have two topics which are both equally likely, and then consider this three words with these different distributions. So here we have the topics with the TS of W1, the highest, because it is almost exclusively for topic 1, but not so much for topic 2. On the other hand, the TS of W0 is 0 because it's equally shared across two different topics. So that's the basic idea. So this is a graphic illustration that how the value of the TS change when the word change. And for the corpus specificity, we directly using the frequency of the word in the corpus. So essentially, this is the easiest calculation. And then finally, we define the salience of a word as a linear combination between TS and a CS. So this is the value which you can select based on your application. Again, the idea really is that the corpus specificity will be high if the word occurs a lot in your corpus, very frequent. And the topic specificity will be high if the word is shared less across different topics. So after we get the salience of the word, we basically perform random walk using the following formula. And here, the only change we made is that now the jump probability was set to the salience of the word WI. So here you see that all the topical information was embedded in the SWI, so we only need to run page run once instead of k times. We don't have to aggregate them, we just run once and we got the score. So this is essentially the basic idea. Is there any question at this point, like on a high level?
I have a question.
Sure.
What is the difference between topic specificity and, for example, the typical information gain extraction?
That's a very good question. So essentially, the topic is to try to capture is that how exclusive a particular word is to a particular topic. It doesn't have to be the KL divergence. You could also define in other ways, like for example, entropy-based measures and so on.
Yeah,
it's totally possible.
Is the way, yeah.
It's totally possible. And actually, that in a paper, I do have a comment that this is actually related to the information gain. If you take an average on words, it's related to the information gain.
It would be interesting to compare the different performances of the two approaches.
Yeah, you can. You definitely can.
Yeah.
You definitely can. So here we essentially we basically face the definition, and what we really compare is when you try to change the alpha parameter. So because you can build in a lot of degree of freedom, let's say. So here, if experimentally, the most interesting thing from our perspective is how the performance of the algorithm changes if the alpha parameter change. The alpha is basically a trade-off parameter balancing TS and CS. Yeah, that's a good point. So it doesn't have to be. The idea really that the key idea really is important to distinguish between topic and corpus specificity. But the exact definition of the two things can really change. For example, I can, instead of using the raw frequency of the word, I could also using, for example, log scale frequency. I could also using TF-IDF-based frequency. That is also possible. Okay, so let's give you some idea about the performance of this particular method. The 500 news and the InSpec are two widely used key phrase extraction benchmark data. The 500 news are essentially news articles, and then the key phrases are provided by the turkers on Mechanical Turk. And InSpec is abstract from a computer science journal where the key phrases are provided by authors. So we have abstract, and then also have key phrases. So this is your data. So the key idea really is that our proposal sentence rank is more efficient because we'll run page rank only once per time. And as you can see that we obtain comparable, or sometimes even better key phrases on the benchmark data. Here is to demonstrate the trade-off parameter alpha. Let me remind you again, this alpha basically try to balance between topic specificity and corpus specificity. And you can see that it does have considerable impact on the performance. And those are the quantitative results. And here I show one qualitative results. So this is the results on one abstracting from the InSpec data. As you can see, when we set alpha to 0, which we focus more on the corpus specificity, that is the frequency of the word in this case, we got a very generic words as key phrases, like for example, function, theory, preference. So if you are, say, not an expert in that area, this is probably the things which give you more information. And on the other hand, if you set alpha to 1, which you want very topic-specific words in your key phrases, you got a very specific key phrases. I mean, for a layman, this Neumann Mungenstein theory probably doesn't tell you much, but for expert, that may be useful. Okay, so here's a quick conclusion about the contribution. The first, as I mentioned, is faster than the state of art because by embedding all the topic information into the word salience, we don't need to run topic one. We don't need to run page rank like multiple times, but only once. And also, one of the important practical implications that is we have this alpha trade-off parameter, which allow you to basically turn your key phrases based on your specific applications. And of course, we should mention some of the applications of key phrase extraction. So here are two examples of key phrase extraction in Amazon. This is we call say browser refinement. Here it's probably a bit hard to see it, but the idea really is that is when you search for something like headphones, let's say, you can basically track key phrases based on the review of headphones, for example. And then those are the key phrases, for example, say good speakers, good sound quality, which allow you to further refine your search. This is another example. For example, this is the similar application to TripAdvisor. When you are browsing one particular product, on top of the reviews, they can provide you the key phrases extracted from the reviews, so you can have to read through all the reviews to get a quick idea about the product. And this is another feature we just actually launched months ago, which is called headphone buying guide. The idea really that is we extract key phrases here. This brings up a noise cancelling, size, and comfort, and help you to browse different browse nodes. For example, if you are searching for noise cancelling phone, those are all the key phrases which customers speak positively about this particular product. And if you want to look at it, you can click on this. It will take you to the selection of product, which is highlighted here. Another feature which is also launched, public testing, is this use case in the comparison table use case, where I'm not sure if it is available in the Luxembourg market, but in the US, for example, if you search for, say, computer, you can see that a screen, for example, it will be shown a comparison table on the detail page. where it can show you a similar product, we can compare on different features of that product. So here the idea is that we have this we call certified customer line. So those are the phrases which is extracted from customer reviews. And here the number is the frequency that how many times the customer talk about it, say positively. And when you click on this particular link, it will take you to the product or the reviews, which is talking about this particular key phrase. And those are all, say, front-end features, but they're also kind of important back-end features. For example, you can think of the key phrases like the search terms. So when you issue a search, the key phrase can be like a search index term. You can use the key phrases extracted as a search term to help you improve the search. This is one example. And also, we work a lot extracting phrases from customer reviews, and this is really from customers. So of course, those information can also be helpful potentially for personalization. Okay, that's actually all from my side. And if you have any other questions, I'm happy to answer.
I have a question. When you compare the performance, which implementation of the PageRank do you use the parallel version or?
Oh, that's a very good point. So this is the standard, just a standard PageRank. So essentially, it's a bilingual PageRank.
Okay, and what about this silent run? It's also the computations that you do. If you go back to the slides where you have a formula, can you decompose that in order to compute it recursively? What are your dependencies on computational in order to elaborate that running block?
Sorry, could you repeat the last part?
Yes. When you set up, when you laid out your formulation of the silence run, do you think, I mean, you can run a parallel implementation in the same way you do it with the PageRank, or there is a limitation in the dependencies between steps that you need to do? Because here you're using the previous step, right? When you do the RWJ there, you use the previous step. So can you run a parallel implementation of this?
The answer to that question is I don't know. Okay. I do think about it because so actually the PageRank is basically an eigenvalue problem.
Yeah.
What the topic of PageRank, which is the approach we're compared to, they essentially say do the PageRank k times independently. But apparently that this actually k PageRank are not independent. Right? I think this is what you're getting to. And this k eigenvalue problem not independent. So the question is, if you say leverage or exploit the structural information, can you make it faster? Right? That's a good point. So I don't really know. But if you like, I point to a paper. I think like 20 years ago, there are people looking at that direction. But I think the message here doesn't change in the sense that in the cities range, you still run PageRank only once per step, right? And the topic PageRank, you have to run k times. No matter how efficient you do, k time is still more time costly than one time. So I think that so in a sense that the message here largely doesn't change.
Okay.
Sure.
What is the difference between the performance of the supervised version for this key extraction and the unsupervised?
Yeah, again, it's a very good question. Normally, in a machine learning setting, the supervised case is always way better than unsupervised case just because you have human labeled data, but not so much in the k-phase extraction. So you do see for a particular application, the supervised case indeed still has a performance better than unsupervised case, but the gap is way smaller than other machine learning problems. There are multiple reasons for that. Because first of all, k-phase extraction is extremely subjective. So if I give an article, let's say, ask you to tell me what are the key phrases for that particular article, ask 10 people give you 10 different answers. So the labeling process is already pretty noisy, so you cannot have a perfect labeling data to start with. And the second rule is that valuation is also very subjective. That's why you often see here that the state-of-art kind of k-phase extraction algorithm has F-score, which is around 0.2, 0.3. That is very low compared with other, say, information retrieval tasks. Right? This is not because the result of the key phases are bad. If you can see here, the result of the key phase is actually pretty okay. So this is low just because the data is super noisy. That's the reason. So to back to your question, that for particular application, supervised case is still better than unsupervised case in terms of pure quantitatively measured numbers, but the difference is way smaller than compared to other tasks. Oh, sure. Another person.
Have you tried how sensitive your performance results are with respect to these heuristics in the beginning?
Oh yeah, that's a very, very good question. I got this question also before. The people was asking, I read another paper. I remember on this particular, because I said that this data set is very widely used benchmark data, right? They said, but remember the number is somewhere around 0.4. How do you only got 0.2? So I think that's related to the question you're asking. This has to go back to the thing I'm talking about here, which this approach only considers the second part. Right? The first part is that you have to first get a set of candidates, right? And that is very, very application dependent. Right? For example, in this particular case, all the result is based on the first one, which we basically select non-phrases using part of street tagging and selected 0 or more adjective and 1 or more nouns. Right? And this is arguably the best choice, or say among the best choice or suitable choice, if you want to mine good key phrases from customer reviews, because you want to select key phrases where customers say something good about your product, then you select the adjective paper. Right? But for scientific paper, it might not necessarily be a good choice. Right? How often you say awesome in a scientific paper? Right? Not so much, I guess. So yeah, they play a very key role. But the question is that well, we want to make this part fixed, so we can concentrate on the second part. That's why everything I presented here is based on this particular heuristic. And if you change to another, it changes the performance a lot. But that is very application dependent, so you cannot say in general which one is the best. Sorry.
So, well, to come back to my previous question, if you have a set of documents, so now you do it per document. Yeah. If you have a set of documents, would that make the task easier?
Yeah, you do. I think you do. How can I say this? So essentially, that here the idea really we want to have a clean setting, right? So essentially, you have a document, this input, and you output the list of key phrases. Now, of course, there are a lot of things can make things better, because for example, if I extract a phrase, my algorithm believes is good based on this particular input, but it doesn't really say much. For example, if you have all the English corpus, you can calculate the language model, right? So in that sense, you can select like a better phrases, right? How can I put it? Is that, for example, you have a key phrases that the two key phrases based on the individual document, they may be equally likely good, right? But if you have the entire corpuses, you could see that based on the language model, this particular phrases appear more frequently in the English language. Right? That gives you better evidence to select that one, because maybe it's more fluent, maybe more widely used. So yeah, so that's an example why it can be helpful.
You also just the combination of the some phrase might be, you might not be sure about a phrase, but if it's appearing in several different documents, you know it belongs together. And
yeah. So having more data, you have more evidence, essentially, I'm saying. And another thing, for example, go back to the application, say, particular application. For example, let's say you want to select phrases from product reviews. You want to have a phrases to describe your product, right? Sometimes you have some other consideration. You want a phrases which is not too unique. In a sense, for example, if you have a product which have the product serial number, right? It is a good key phrase for this particular product, but doesn't generalize well to other products, for example. Right? So these phrases may be not useful if you consider a set of things together. But this kind of information help you also filter out the things which is very specific. Does that make sense?
Yep.
About the calculation of the word relation, you said that it's calculated through a sliding window.
Yeah.
Is the only known way to do from, because it seems that you could miss a lot.
Yeah. So I have so in this particular setting, what we do is that we have a sliding window. We basically just walk through the windows, and then to walk through the documents. Whenever two words appear in the windows, we have a link there. So there are many things you can do there. First of all, that what about the size of the windows? Right? Empirically, actually, it doesn't change the performance too much. So if you have a size of windows of 5 or 3 or 10, it doesn't change the performance too much. This is one thing. And the second thing can be interesting here is if two words appear, right, and how often they appear. Right? So if the edge has a weight or not. You can also do some kind of weighted page rank or a non-weighted page rank. In our cases, we simply try to binary. So there's a link, then there's a link. We don't have any weight on that link. And we also run some experiments. There are some differences, but it doesn't really change too much. So when you do, especially when you do quantitative analysis for some particular research, you want to as straightforward as possible, because otherwise you need too many degree of freedoms and make it a comparison very difficult. That's why, because it doesn't change the performance too much, so we only have a binary link. And another thing, probably not that related to your question, is that this is a question I also got a lot, is that in this approach, and similar to other approach about key phrase extraction, we essentially make assumption that the key phrases you extracted are always the phrases you appear in that document, right? Imagine that you have a phrase, say, great Amazon, let's say. And if a great Amazon is a good key phrase, then I think good Amazon is also a good key phrase, right? Because good and great are basically the same. But most of the approaches stick to the raw text. So we don't do that particular extension. There are also work trying to, for example, find the phrases which can be related using, for example, WordNet. The WordNet is basically kind of like a huge dictionary which have relation between. There are also people trying to do that. For example, if I have, say, good Amazon, good key phrases, I also automatically say good Amazon also good key phrases. But in this particular work, we don't consider that.
I was thinking, what do you do with you have the topic, the models of the topics? Where do you get those from?
Oh yeah. This has to do with the topic modeling algorithm. And so, in the topic modeling algorithm, you essentially predefine before you run the topic modeling. You basically say you define how many topics you want to have. Right? Let's say you want 5 or 10 or 20, and you run. And then what the model does is basically find out the best clustering. Essentially, it's a kind of a clustering. The best, say, topics which describe you documents. And here the topic, when I say topic, is strictly in a statistic sense.
Yeah.
The topic is just a distribution over words.
Yeah.
So you don't need to specify, is this topic for movies or not? It doesn't really matter. It's just a statistical tool for you to get some structure from your documents. Oh, sure.
Can you differentiate topic and subtopics?
I see. No. The reason is that we are using topic modeling, and so as the topic page rank, we're using LDA. In the LDA, just like overall clustering, so you say how many topics you want. I give so many topics. So there's no subtopic, so to say. But of course, you can get fancy here. You can using this Chinese restaurant process, and you can get like hierarchical topics. This is possible, but we don't do that here. You can. Okay.
But it's possible that the search result of your algorithm, they are all about the same. Actually, it's one topic, just different aspects of the topic. Right?
That is possible. That would be, if that happens, that is because you run the topic algorithm. You have the effect in the topic modeling LDA. There's a known effect we're calling. It's called a winner takes all. And one of the topic gets bigger, bigger, and bigger. Then the other topic becomes smaller, smaller, smaller. But not in our case, because we basically initialize the topic in the sense that all the topics are generally overly, like more or less equally likely. But this is a known issue in topic in LDA. But there is also a way to address that.
Okay, thank you very much.
And before we let you go, one word about machine learning. I completely forgot about machine learning core team. They're hiring. If you really hate Luxembourg, they're hiring in Berlin. They're hiring, I think, in Barcelona. You opened it recently.
Yeah, and in Cambridge too.
In Cambridge, and if you really want to go away from Europe, they have huge team in Seattle. Yeah.
Yeah, sure. Yeah, I know Cambridge too. Now it's not Europe. So.
Yeah. Meanwhile, if you really love Luxembourg, I have a proposal for you as well. AWS deep learning team hiring as well for Europe in Luxembourg or other big city like Munich, Berlin, or something. So if you're interested, either you go Amazon.jobs or you can contact me, and I will help you with that. Thank you again.
Thank you.
So, yeah. Okay. So now
It's on the desktop.
yeah. So you can go. Try this. Knowledge. Yeah. Yeah, good.
Okay, so thanks a lot for the invitation, first of all. As Zita said, I'm currently working at the Publications Office of the European Union. Anyway, I'm still, let's say, related to and associated to the Italian National Research Council, in particular to the Legal Information Institute, which is in Florence. And this work is the result of a research activity within the ITIG Institute of the National Research Council in Italy. So this is about modeling legal rules for advanced access to legislation, but you can consider legislation in more broader sense, like normative documents in general. And so the aim is to try to find or to develop a system that is able to to improve the access to legislative documents for the end users. Okay, so actually the legal domain is a specific and challenging domain for the implementation of the semantic web concept for several different reasons, for the complexity of the legal domain itself and for the peculiarities of the legal user information needs, be them laymen or professionals. This is a possible scenario in which this system can be useful. Let's consider a citizens that want to subscribe an online contract, like, for example, buying something in an e-commerce website, or, for example, buying a service from a public administration. He might be interested in to know which are his rights and which are the duties of the counterpart. So in particular, they might be interested, for example, in consumers' rights, for example, which are the right of withdrawal, the supplier duties toward the consumer, and in particular, which are the implicit rights of the consumer itself. And moreover, which are the procedures to fulfill the consumer duties and the sanctions in case of non-compliance. So the aim is actually to allow citizens not only to access the full document, which is not so interested in the legal domain, but to access to the single provisions. So to know which are my rights, I would like to know that. I would like to read just the paragraphs that pertain to my information needs. So the semantic web can be a solution for the implementation of a system that allows you to implement an effective tool for responding to this need. So what we have tried to implement is a system, retrieval system of norms endowed with reasoning facilities. First of all, let's say that we can say that this system is based on some legal theories that considers laws and regulation as seen as a set of provision, as I've previously said. Let's consider, let's say, a document just like a vector conveying different provisions, which is something that is really interested by the end user, which is carried by speech acts. So a legislative text or a normative text in general, like for example a contract, can be viewed according to two different profiles. The so-called formal profiles, so the text paragraph, the text can be organized in terms of chapters, articles, paragraphs, and the so-called semantic profile, which is the text organization according to the partition substantial meaning. Actually, this is something not specific to the legal domain, but typical to every document. For example, a scientific document has can be viewed according to the formal structure, so a set of sections, but also from a point of view of its semantics, like for example, one section might contain the introduction, the other section might contain the conclusion, another section contains, let's say, the core topic of the document itself. And the same is for a legal document. You have usually articles that contain paragraphs, and these paragraphs contains specific provisions, like for example, obligation, permissions, sanctions, definition of specific terms, and so on. And so we are interested in knowing and in accessing directly to the part of the text that pertains to our needs. So this semantic profile in particular can be represented in terms of normative provisions. Let's consider, for example, this excerpt of a European Union directive. It can be viewed, as I said before, in terms of formal profile as a set of paragraphs. But what is much more important is that you can look at it as in terms of its semantics profile, which contains, for example, duties for the suppliers towards the consumer, or the procedure of the suppliers with respect to the consumer to fulfill a specific obligation, or the right of the consumer with respect to the supplier, or the duties, for example, of the member states towards the consumer. Here, basically, these semantics have been written in terms of functional notation, but in the next slides, we have implemented it according to the semantic web technologies. Let's say the semantic profile of a legal text can be considered not only at this level, or let's say in terms of provisions, but also in terms of provision types and attributes, which is a specific sub-profile, which is we called it as functional profile, which is actually common to every normative document. Every normative document has usually a duty, and each duty can be described with a specific semantic structure in terms of a bearer, of action, of object, and of counterpart. And that's the so-called thematic profile. The thematic profile is actually the topics which are related to that specific document. For example, the fact that in a particular partition, in a particular paragraph, you have the description of the duty of the bearer supplier, which has an action, has to communicate the contractual terms to a consumer. And this description can be given in a formalized way so that it can be queried, it can be retrieved using a particular structured language like Sparkle, as we can see later. So the aim is to describe the semantic profile of normative text in terms of functional profile and thematic profile. So actually the provision model, what we have seen before, can be considered an effective implementation of the so-called legal semantic web. As well as in the semantic web, we pass from the web of document to the web of data. Similarly, in the legal semantic web, you can consider to pass from the web of legislative documents or normative documents in general to the web of normative provision, which are the real important aspect that we would like to know. A provision-centric view of a legislative text contributes to several aspects in terms of transparency, because your text is more accessible to the end user for a search engine, can improve the semantic search facilities based on norm, can provide advice to the consolidation. So, for example, you know that in the institutions, like for example in the parliament, you have the need to consolidate the text in terms of how an amendment can affect a specific portion of a text, like a versioning, let's say. And so describing the amending action allows you to provide the consolidated text in an automatic way. Moreover, you can have the analysis of coherence and impact of new text of on the legal system, like discovering contradictory norms or regulative impact analysis. Finally, some other possible implementation that are more oriented to the public administration and future, let's say, application can be the so-called legal drafting based on semantics. So a legal text can be actually written from the point of view of semantics, the point of view of its semantics. Let's say you can say, I want to describe a duty for the supplier towards the consumer. I just include in a visual panel this visual object, and I can generate the text just at the end after the description, the semantic description of its content. In this specific presentation, we actually describe an implementation that is very much specific for a semantic search engine or for the analysis of coherence and impact on new text, but can be used for other different purposes. One of the main aspects is, in particular coming from the legal theory, is the fact that what would be important is to know not only the rules that are explicitly written, but the rules that are also implicitly induced. So, or deduced, let's say, from a text. This comes from specific legal theory like the Offeldian relationships between norms. For example, according to Opheld, which was a legal philosopher of the beginning of the last century, you have a relationship between specific type of provisions. For example, if you have a right of a bearer towards a consumer, it means that the consumer has a duty with respect to the bearer. And if I am a specific citizen and I want to know which are my rights, sometimes my rights are written in terms of duties of the counterpart. So it would be interesting to retrieve, just to write in, let's say, a query, please give me my right, and the system gives you back not only the rights that are explicitly written, but also the duties that are that affect your rights. Okay, so for example, we have the so-called Offeldian square, the first one on the left, which contains so-called deontic notions. is coming from legal theory, so I have to say that. And the other part are the Opheldian square related to the so-called anancastic provisions. But the same, let's say the concept is still the same. You have a relationship between rights and duties, like power and liability. So if I have a power towards you, it means that you have a subjection towards me, so a liability towards me, okay? And similarly, you have a similar relationship between these provisions. In the text, you can have also technical relations, which are not necessary. While the previous relationship, the Opheldian relationship, are typical of every text. So in every text, you have duties, and if you have a duty, it's necessary that you have also let's say, the specular aspect. So the aspect of the right, okay? On the other hand, the second type of relations are not necessary from the logical point of view, but are established within each specific text. For example, the fact that you want to describe a specific procedure in order to fulfill your duty. Okay, so this relationship between the duty and the procedure to fulfill this duty is something that is written directly by the drafter. It's not necessary that these two provisions are related one to the other. For example, the fact, as I said, that the duty of a bearer to accomplish a specific action towards a counterpart, or the procedure describing how to fulfill such obligation, or the exception to it, or the sanction that such bearer may face if he does not fulfill such obligation. So all these relationships are technical relationships because are established at the moment of in the text, are not at the level of the model. Okay. While the previous, the logical relation, are relationship at the level of the model. So, so basically, the system that we would like to implement is a system in which the citizens can query in terms of give me my right, and the system can. For example, I'm a consumer because I have subscribed a specific online contract. I want to know which are my rights, and the system can gives you back not only the right explicitly expressed, like this one. I'm a consumer. I want to receive back my rights. I want the system might provide you back also the duties in which the consumer is a counterpart, because they are actually right of the consumer, okay? Even if they are expressed differently. It's like having a sort of direct or indirect way to express the same concept, active or passive way to express the concept. The same for technical relation. I want to know the duty of the supplier to communicate contractual terms, and I can extract also the procedure how to accomplish this duty. So the approach is based on a representation of the provision types and attributes in terms of the provision models. Moreover, the need is how to express axioms on provision types and attributes. And the tools that we have used are RDF schema and ALDL standards, so ontology web language, in particular the profile of OWL, which is based on the description logic, because it's computable. No, it's you have reasoners that allows you to implement in a finite time this sort of reasoning. And then Sparkle has query language. So this is the provision model top classes. Basically, you have the top class of provision, which is which has subclasses like rule and rules on rules. Rules are basically regulative and constitutive rules, or the amendments. And in particular, as for regulative provisions, you have permission, prohibition, duty, right, violation, redress, and so on. And so you have this sort of taxonomy of provision types. And each provision type have a specific model, so a number of specific properties, like the fact that a right has a specific bearer, has a specific action, has a specific counterpart or an object. And the same holds for the duty. The bearer, the action, the counterpart, and the object. So it's sort of a set of slots of, you can look at them as metadata, as in several different ways. The values of such metadata, for example, who is the bearer of a duty, can be expressed in terms of literals, so just text, or concepts coming from an ontology. So like, for example, a URI that point to a specific ontology that can be external to the system. Like, for example, the Dalos consumer law ontology that we actually have developed within a European project. So how to represent, in particular, logical relationships, the relationships that are at the level of the model. In particular, the Opheldian relationship between duty and right. If you express them in terms of functional notation, you have that a duty has bearer supplier and a counterpart consumer, and it is in relationship with the right of the consumer, who is the bearer here, and the supplier, who is the counterpart. So at first sight, you might consider that there is a sort of equivalence relationship between duty and right, and has bearer and has counterpart. But this relation drives you to misleading conclusion. The fact that, for example, a duty which has a bearer supplier is equivalent to the right which has a bearer supplier, which is not true, obviously. And the same for the duty. The duty who has a bearer supply is not true that is equivalent to the counterpart, to the duty with a counterpart supplier. So this is a misleading conclusion. So the way our objective was how to implement this relation between duty and right when, let's say, they share the same bearer and the same counterpart. So actually what we have to consider is that a right or a duty in relationship with it is not actually expressed in the text, but is something that is implicit. So if you have a right, you read it as a right, but implicitly you can read it as a duty. So you actually can express, let's say, this relationship in terms of implicit right and explicit right, or implicit duty and explicit duty. So the equivalence that you can express are actually the equivalence between an implicit right, which has an equivalence relation with explicit duty, and an implicit duty which has an equivalence relationship with the explicit right. Similarly, you have similar axioms for the attributes. So we have an equivalence relation between the bearer of an implicit duty with respect to the counterpart of an explicit right. And similarly, you have an equivalence relation with the counterpart of an implicit right and the bearer of an explicit duty. So basically, in this way, you have the possibility to establish relationship between implicit and explicit norms. So this pattern, which can be repeated for every type of relationship of the Opheldian squares that you have seen before, have several properties. For example, when you, let's say, express a query, you don't need to express a query in terms of a conditional statement. For example, you don't need to say if has duty counterpart is consumer, so give me back his duty. You have, let's say, a direct way to express and to extract the specific information required. Moreover, you use abstract classes, like implicit classes, for expressing the relationship between the norms. Actually, the benefit of the approach is to keep the problem within the RDL complexity, which means that you can use existing reasoner for implementing inferences on the model in a finite time. For example, we have implemented this system using an OWL reasoner like Pellet, which is a Java-based OWL reasoner, and the result is a provision model where inferences are calculated from the asserted actions. So let's have a look at how it actually works, this system. So you have, for example, the previous 3-4 provisions. You have on the right the description of this provision in terms of RTF. So you have the description of the explicit duty, of the procedure, of the explicit right, and of the explicit duty again, with the specific properties in terms of supplier, consumer, member state, consumer, and so on as a counterpart. As you can notice, basically here, only the explicit provisions are used for the markup, for the annotation, because it is actually what is written. What is written is what is explicit. You use implicit concept just for reasoning and for obtaining the inferences that I previously mentioned. So let's have a look at some examples, and then we go on with the NLP and machine learning aspect. So how to implement actually the semantic annotation of this document. So let's consider this Sparkle query using provision model and ontology concept. This query is just a Sparkle query in which you basically require to retrieve back a provision, which is this variable, having has a bearer of a right the element consumer. So I want to know which are the right of the consumer, which is our query at the beginning. So just including this query in your system, you can query, for example, this set of provisions, but here you don't have any right of the bearer. You have explicit right, okay? But obviously the system doesn't understand the fact that explicit right are in a sense related to the right of the bearer. And in fact, if you make a query on the asserted model, you know, inferences in the ontology domain, no? Basically you can derive implicit knowledge from the reasoner. So if you query the system on the asserted model, you have no hits, so you don't retrieve nothing. But if you apply the reasoner to your system, you have the possibility to extract, to select the explicit right, because it is actually a subclass of the rights, but also the explicit duties, the first and the second one, because they are in equivalence relationship with the implicit right, and they are actually implicit right, like this one. You can do the same for other, let's say, examples, but I don't want to bother you much more on this. So let's have a look on, okay, this the prototype of the legal search engine is called the Promise, like a wish for the future, provision model-based inferential legal search engine. This is actually the architecture of the prototype of the system. So which are the benefits of this approach? The advantages are the fact that you use patterns that you can repeat them, you can apply on different specific relationship. And moreover, one of the advantages is the computational tractability. In the semantic web domain, there are lots of efforts to try to find the specific, let's say, languages in order to implement, for example, conditional statement like SWIRL, like semantic web rule language, or REEF, or XML description of the rules. But if you stick to the basic technology, and if you are within the ALDL, so the description logic framework and environment, you are able to implement this system in a finite time and with an effective, let's say, effective performances. Which are the problems? Obviously, the burden of the semantic annotation of the document and the knowledge acquisition bottleneck. And it's what actually, if I have still some time, to address with this second part of this presentation. So how we can actually implement a semantic annotation of the legal document in an effective way. Okay, you have two different approaches. The top-down approach, which is actually the semantic annotation, which is maybe the most that can be viewed for the future, like having, like I said at the beginning, an environment that allows you to think of a document in terms of semantics. So in a visual environment, using the provision model as a semantic guide for planning a new bill. So you can write, not just writing text, but just taking semantic objects and making relationship between them and then regenerating the text at the end. But currently, you have another possibility. Since the texts are already there, for example, for legacy content, you have the possibility to implement a bottom-up semantic annotation, which can be manual, but it's a burden for the annotator, or automatic or semi-automatic, like using automatic classification of provisions or provision attribute extraction using, let's say, machine learning and natural language processing approach. So let's have a look at the semantic annotation bottom-up approach. It is part of a set of tools that is called the XMLedges family. It is a drafting environment which is thought particularly for the public administration, but it contains the tools that I have mentioned before, like, for example, semantic managers, like the classifier of provisions or the extractor of the provision properties, like bearer, counterpart, and so on. So for the classifier, first of all, one of the possibilities is to consider, let's say, a normative text, and the aim is to classify each portion of the text in terms of provision model. And actually, the classification of paragraphs according to the provision types is a problem of document categorization, so classification of a document. And we have tested two machine learning approach of text categorization, like the knife-based approach has a generative approach for machine learning, or support vector machine has a discriminative approach for the same problem. First of all, we have considered a paragraph as a document, and we have, let's say, described each document as typically done as in terms of a vector of term weights, and using three different types of weights, in particular binary weights. So we have considered the presence of or the absence of a term within the document, considering starting from a vocabulary that can be built from your data set. Then we have the possibility to describe each terms in terms of term frequency weight. So you actually count the number of time a specific term of your vocabulary appears in that particular document, or the typical TF-IDF weight schema, which, as you know, penalize terms occurring in many different documents being less discriminative. No? So if a term appears in all, you well know this, but if a term appears in all the paragraphs or in all the document, it means that it is less discriminative than others. Okay. Other pre-processing of terms have been considered just to increase the statistical qualities of terms. In particular, the stemming, so the reduction of terms to the morphological root, which works quite well for English, less well for other languages. The stop word elimination, so the deletion of very frequent terms, because they do not provide interesting information, because if a term appears everywhere, it means that it is not so discriminative. And digit and non-alphabetic characters represent a unique special, is represented by a unique special character, because it doesn't provide semantics in terms of provision types. So the fact that you can, in a document, it is contained a date or a number, this doesn't provide the specific semantics for a duty or for an obligation or for a permission and so on. And so we consider those terms like a unique single character. Then we have implemented the feature selection in terms of information gain that we have discussed before. First of all, using an unsupervised minimum frequency threshold, aiming at eliminating terms with poor statistics for the reason mentioned before, and the so-called supervised threshold over the information gain. The information gain is a very interesting measure of the discriminative power of a term. Basically, you can consider that if you have a document, a term and a class, if all the term belong to, if a specific term belongs to that specific class, it means that its let's say informative power is very high. So it means that let's say let's say the entropy of your data set is very limited, is very low. So it means that the entropy associated to a term is low, and the information gain of the term is very high. So the discriminative power is very high. So basically, if all the document belongs to a specific class, and they contain those documents, and only those documents contain that terms, it means that these terms is very much discriminative for that class. And so I want to keep them, okay? In the experiment, we have considered a data set of more than 500 examples, so fragment of pre-labeled text belonging to 11 different classes of our provision model expressed before, like repeal, definition, delegation, delegification, duty, and so on. And we have here the number of documents for each type. So for the knife-based approach, using the full text paragraphs, the paragraph full text, sorry, we have had a train accuracy of 90% and a so-called leave one out, LOO means leave one out accuracy of 86%. Leave one out means it's a methodology for testing your training. Basically, with the leave one out, you use your training data set for testing, except one that you use for the full data set for training, and you use just one of your example out of the training set to test the generalization capability of the system. And you repeat this for every single examples in your data set. And then you collect the results in order to obtain the final so-called leave one out accuracy. This is typical when you don't have a so large data set and you cannot divide your data set, let's say, in 60% for training and 40% for test. You use the 100% to train, except one example that every time you use for test. You leave it out of the training set, actually. That's why the name. There are other particular provisions that contain, like the amendments, that contains quoted text that basically is a misleading text, because it doesn't this text doesn't tells you anything about the fact that that provision is an amendment. In terms of semantics, is related to another provision, the provision that is amended by the amendment. Okay, so the quoted text can the quoted text can be cancelled. Yes, I've basically finished. And so we have a leave one out accuracy of that increase to the 88%. And then we have with the SVM, support vector machine, we had better results till 92.1% in the test. From the point of view of NLP, so natural language processing, we have used a specific representation of the text in terms of chunking. So basically, terms are described in terms of their function in the text. So, for example, subject, object, or other specific role of the components of the text. And so with the chunking, we had much more even better results, 92.7%. So this is the comparison between SVM with chunker. It's written in Italian, sorry, so it's SVM without chunker, SVM without knife base without chunker. Finally, for extracting the elements, so the different let's say actors or values of the provision attributes, we have once you have classified a provision as, for example, duty, you want to implement a system which is model driven that tells you, give me, please extract, since this is a duty, I want to identify the bearer, the action, the counterpart, and the object. And using NLP processing, we can retrieve the specific provision attributes. And we obtained a total success of 82% in this respect. And this is the workflow of the system. You have, first of all, the tokenization, the morphological analysis, the chunking, and then we apply the classifier, and from the classifier and the model related to a specific provision type, we extract the provision elements, provision attributes, and we obtain the annotated text. So basically, this is the approach for using the provision model and semantic web technologies and machine learning and natural language processing for implementing this service. And that's all.
Questions. what are the next steps on this work? What are the results after this approach, as you put it?
Yeah, actually, the next approach would be to try to implement, not from a point of view of a laboratory experiment, as we did, but just in a prototype, which has not been implemented yet. So it's actually what we would like to do. And maybe testing other machine learning approach for classifying a text, for extracting these terms. One of the main aspects of the new trend of the semantic web is that you can rely on, let's say, the so-called linked open data movement. So now, with respect to some years ago, you have lots of data available already annotated according to, for example, in XML. And so you have already the first step of the approach available. Let's say, for example, at the Publications Office now, the European Union, you can have access to all the legislation in terms of XML. So you have the paragraphs well identified with a specific URI, and so you have the possibility to link to each specific portion of the text a classification or a semantic annotation. So we hope that, let's say, the linked open data approach, which is a bottom-up way to implement the semantic web, can stimulate, let's say, the consumer to implement additional services. For example, like this one. Like, for example, some commercial publishers or legal publishers that might be interested to provide to the final users this sort of service, which is something different with respect to giving them a search engine which just retrieve back the documents. In this case, you retrieve back the provisions, which is something very specific to my needs.
Did you consider to represent the causality when you are representing the law or regulation?
Causality in terms, in sense?
If you are, because when you define the concept, you are talking about various actions.
Yeah.
So you have the causality of an action. Do you use it to define implicitly rights or implicit abilities?
Yeah.
And do you have a model to represent this causality?
Not for now. Not for now. But actually it can be implemented for sure. The only problem is that, as we have seen here, it's a burden to implement this kind of annotation. That's why it's important to rely on machine learning, on natural language processing, on linked open data approach, which is basically the way how to obtain the document in a structured way. This is something that can be done for sure, but it's something more related to the modeling part. This is the typical approach that we have to implement, involving, for example, in our case here, legal expert. Which is because this work, for example, comes from the interaction of previously expressed theories and the implementation of them with semantic web technologies. So this interaction can be fruitful, usually, we hope.
So you give one label to paragraphs, if I understand correctly. Is it general legal practice to really split it up, or is it really mixed up in practice?
No, this is a problem on which lawyers can make money, because this is a way to, let's say, to say that these paragraphs can be can have different meaning, can have a blurred interpretation, and so on. What is the aim of this tool is not just to provide the truth of what is written in the text, but just to provide a sort of a hint or an advice for the final user that wants to get oriented in the large amount of regulation on a specific matter, for example. And that can be useful for the layman as well for legal professionals. But it's not meant to give you the truth, obviously.
But wouldn't it make sense then to give two labels? If you're unsure to give two labels, you can have two paragraphs.
Yeah, this is it's possible when you let's say because usually also the legislator doesn't include a provision just in different more provision in different paragraphs, but sometimes they include two provisions in the same paragraph, and actually is something that should be avoided. Actually. But you can actually label the provide labels or multiple labels to each single paragraph.
How do we deal with references? Because when I remember context, they have a lot with exclusion of paragraph 1, something now.
Actually, in this set of tools that we had, in this set of tools, you can see. Here we have illustrated now the semantic managers, so the tools that are able to deal with semantics. But there are two other tools which deals with the structure. So they are able to transform a plain text into XML or whatever standard you wish, and to extract references. The so-called linker, XML linker, is the automatic hyperlinks extractor. So it is based on Lex and YACC technology, yet another compiler technology, and Lex is basically the way how to extract tokens. It's quite interesting tool because it's very effective, but it's also not so big effort, in particular for the legal domain, because the way how the references are expressed is very, let's say, typical. So you have a typical way to express a reference. Article 2, paragraph 1 of the law number XY, and so on.
So do you model these references as relationships?
Yes, because in the project that from which this approach derives from, it's a project of dealing with the Italian legislation in particular, where we have defined a way how to describe legal reference using URN technologies, and also now with the new approach, HTTP-based standards for describing legal references. There is an initiative which is the URN Lex, which has been submitted to the IETF, International Engineering Task Force, to obtain, let's say, the definition of these standards as a official standard for legal reference at the international level, so that this standard can be part of the internet protocols at the end.
Mm-hmm. But does your inference engine, which you presented in the beginning, does that take into account these links, or
no?
Okay.
No. This doesn't take into account the links. But I agree with you that this can be an additional information for extracting relationship between documents. But for now, we have just used plain text, and the results are quite interesting. There is room for improvement, that's for sure.
presentation, and before we go to enjoy our